graduate student of the department, and he is going to talk on ribbon categories, which are invariant generating machine. So he is giving 2 talks. This is part 1.
Hello. So yeah, as she said, today I'm going to talk about ribbon categories. So before going into ribbon categories, I would like to show you something. So if G is a group, then there's a natural way to look at it as a category. So you take a category where you have one abstract object which is just a point, and then for every element of the group G, I'll put a morphism from that object to itself. So every element of G is going to be a morphism from that object to itself, and then I'll say morphisms should be composable in every category. So the composition of these 2 morphisms G and H, I will represent it by the product. So inside G I have a product, and I'll say G composed H is same as the morphism which is given by the arrow of GH. So in this setting, the identity of the group G will give you the identity arrow, which is so it satisfies all properties of a category, and so there's a natural category structure with just one object. Given any group, you can construct such a category. Now if you look at the category of vector spaces over a fixed field, now let's say I call this category to be G tilde. Now if I have a functor from G tilde into category of vector spaces, then that is going to send this special object to some vector space over there, and then every morphism over here will go to some morphism of the vector space. Since every element of G is invertible, the morphisms there should be invertible, so every element will go to an automorphism of the vector space. So what you get is that the image of that special point is some vector space V, and that V becomes a representation of G. So this is a nice way of looking at representations of a group. So in this way you can realize a functor as a representation. So this is the point that I want to stress. So here we are going to look at something called the ribbon category, and then we will treat a representation of this category would mean a functor from this category into some nice category. So yeah, so this is a way to generalize representations. That's what I wanted to say. So today's main protagonist is this guy called category of framed tangles. So how to look at these things is like, so you take a cube, so take a cube and then identify two faces as like, so I'll call this face as F1 and this one as F0, and so basically a framed tangle is going to be a tangle which is made out of a ribbon. So this is literally like tangles which are made of ribbons. So as Professor Ilya Kaufman said in the lecture, like you can keep one tangle over the other and you get a new tangle. So we are going to use that structure. So objects over here are going to look at so for every n and m integers, maybe natural numbers, so you fix m for n. I will choose n line segments which are parallel to this axis, and then m ones over here, and then I can say every nm tangle, which is going to be a tangle. So I should draw an example of a tangle. So for example, this is a 3-1 tangle. So there are 3 points over here and 1 point over here. But if you make a tangle with a ribbon, then instead of points, you will get line segments. So these line segments are going to be precisely these. So I fix a set of line segments on these two faces, and I'll say all my tangles that I'm going to construct are only intersecting at these line segments, these special ones. And then all these line segments can be oriented in exactly two ways. So I'll say this way is negative and this way is positive. So this is my positive and this is negative, and on the below face I have to reverse the orientation for a certain reason. So so this will be a 3-1 tangle. So for every n and m I have fixed these things. Now now you can see that, like, if I have a okay, I'll draw a tangle inside. So it's very difficult when you draw like this, like you have to visualize these things as, so these line segments are going to be perpendicular to the plane of the board, and the plane of the ribbon is really a perpendicular plane. It is not a plane parallel to the plane of this board. Okay, but then it's difficult to draw such things, so you have to imagine what I am trying to say. So yeah.
Tangles are basically similar to braids, but just like in braids
You allow tangle to go up also. The braids are always like the height function is monotonic. Yeah, here you allow all sorts of possibilities. Okay. Yeah, but the intersection should be only on these two faces. You can't intersect on these faces and all, like only on the special two faces. Those are called framed, and then you're looking at the framed ones. And these are framed oriented tangles. That means that so they are so I will you can define them as embeddings of rectangles, and also you can see that there can be something like a annulus inside this. So these kinds of things can also be there as a tangle. This is also a tangle. So I would define it as an embedding of a finite family of rectangles and annulus, so that the intersection of each rectangle on this cube is only on the face, and only on the only two sides of the rectangle intersects. Okay, and then the you don't allow these things to be half twisted. So you don't allow Mobius strips, and so they should all only have full twists. Okay, these are some technical reasons. And
this annulus that you've drawn could not have a twist.
So it's an embedding of a cylinder, so it cannot have twist. It will always be a cylinder, so you cannot make a Mobius strip out of it. But these ones should not be half twisted. If you twist, it should be a full twist. That's all what we say.
The annuli cannot be twisted?
No, you can't. You can twist it. So annulus embedded into that can have full twist. So that's okay. Yeah.
But no Mobius.
No Mobius bands. So that's the only.
So instead of annulus, can you have like a knotted ribbon in that?
Yeah. It's also an embedding of the annulus. So
What's the requirement of projecting to the vertical rectangle?
There are, so you can have this framed like isotope, I mean framed moves, no, like, so when you draw such diagrams, we are always considering up to these like isotopies that there are framed Reidemeister moves, like it's a set of very big set of moves.
If you take a framed tangle in a rectangle, like I was doing,
Yeah.
and cross it with I,
Yeah.
you'll get one of yours. But I assume you can allow more general things.
You don't. You take a usual tangle and then cross it with
You
I.
just thicken this way.
Okay. Yeah.
But it seems like you're allowing some more general things, right?
These annuli.
I can ask later.
Okay.
Your these ribbon, they can also have a twist?
They cannot have half twists. So
Can you just show us?
so a half twist means that if you take a ribbon like this, and if you are going to embed this, like this is fine. But if you make just a half twist and then embed it, this is not allowed. If you are twisting, you should make a full twist, and then only put it. Okay. So full twists correspond to this.
The left edge should go to the left edge, and the right edge.
Yeah, the edges should be, the orientations are nicely preserved. So if you try to orient a rectangle, then you see that it will uniquely determine an orientation on the boundary, and this is a point that you should notice. So so if you orient the rectangle, so you choose one of the faces to be towards you, so then this gives an orientation on the boundary, and this will be like this. Okay, so these two are in the opposite directions. So this will come up a little later. I want you to notice this, and
The orientation for the ribbons or for this.
these ribbons are oriented, like they are surfaces when with some chosen orientation.
And what do you mean by those orientations of the cube? Like you're saying,
Of the cube?
yeah. Did you say?
No, I didn't
the
say
top
orientation.
rectangle
Huh?
and the top rectangle and the bottom one. Or
Yeah, you identify the cube as a I3 product of intervals, and then you identify two faces like uniquely. So you choose this product.
Those line segments.
Yes. So these line segments. Yeah. So you fix these line segments. So tangles can intersect in any line segments, but then you're fixing these line segments, and then that's for a reason. Like we'll see, to compose them you need to fix these line segments.
It's fine, but they also have a.
Yeah, once you fix them, you can there are only two orientations on them. So they are perpendicular to the plane of the board. So either this orientation or this orientation, and this one you call as positive. You reverse it because you want to compose them.
Because that one, what is the for this tangle? What is the restriction? Like we should go from top to bottom, or they can. How are we having one circle in between?
So a tangle should be really thought of as a part of a link which is inside a cube. So it can have such structures. So you can have a framed link whose part who has this kind of a part inside a cube. Yeah. So
You said that it should be a family of rectangles.
yeah, a finite family of rectangles and cylinders.
And cylinders.
Yeah.
And disjoint family.
It is joint family. Yes. Right. So yeah. So one observation is that if you have an NM tangle and then an MK tangle, so that their orientations match on this on the below face. So the orientation of these M1s match with the M1s in the beginning. Then you can keep one over the other. So what I'm talking about is like suppose you have a tangle like this, and then let's say this is your tangle, and then suppose you had another tangle of this form. Then you can keep one over the other, and then you can get a longer tangle, and this also belongs to the same kind of object that you have started with. So this defines a composition of tangles. So then so you can see where I'm getting at. So there is so FR tang, we will treat it as a category where objects are going to be finite words in 2 letters. So my objects of this category are words in on 2 letters plus and minus. So that determines the orientation on the line segments, and then given any 2 words, I look at tangles between them, connecting them. So the arrows of this category are going to be the tangles, framed tangles which connect them. Yeah. So now if you see, like if I am looking at 0 0 tangles, then those are going to be all the framed links that you can ever have, right? So every framed link will be a morphism from 0 to 0. So in this philosophy, I would like to represent this category over some algebraic categories, and I would like to get some information about links which are invariants. So it's very reasonable to ask for representing this category. But then the idea is that this category is not just any category, it has much more algebraic structure. So to look at the algebraic structures of this category, I would like to take a little bit of digression and introduce some structures on categories.
So 0 means no ribbon.
0 means no line segments. There are no line segments. So in between there is a space. So you can have any ribbon which is embedded so that they don't intersect the boundaries. So if you look at this annulus over here, it's not intersecting the boundaries. So any
But
The
0 is not
parameter
a
doesn't
line.
take care of the number of embedded annuli, right?
no, yeah, and the annuli is not complete. So that is why no. So between 0 0 you can have as many embeddings of the annulus.
Yeah, so all kind of links.
Yeah,
All kind
all
of
framed
components.
links.
Can we say that the line segments which you draw on the top and the bottom sides of the cuboid, that they are identified to each other? So you can say that the link is closed.
You can do that, but then I mean that's not the only way to close that, no, like.
Like the link which you've drawn like this.
So right now they are not identified. Like it's just that we have chosen a set of lines for every n and m. Like we will have a chosen line segments there with a certain orientation, right? So yeah. So now let's look at the category of vector spaces over a fixed field K. Yeah, mostly.
So over there, like the arrows you are saying they are the tangles. So objects are like depending. So are you determining the tangle depending on this plus minus sign? Like is it dependent on?
No, it's just a matter of the orientation. So once you orient, there will be pluses and minus. No, you can orient in a different way, and you can get different words.
But we can for the tangles like the ribbon can go from plus.
The same tangle can represent different words in the when you change the representation, when you change the orientation.
Okay.
Yeah, it's just a matter of how to orient them. So in the category of vector spaces, what you can see is that it's also a category, and the morphisms are your vectors, linear maps, and but then there is an operation on this category which is called the tensor product. Given any two vector spaces, you can tensor them and get a new vector space, and given any two morphisms, you can tensor them and get a morphism in the category. And yeah, and there is an identity of this tensor product. So given if V and W are vector spaces, then you have a vector space called V tensor W, and morphisms can be tensored, and there is an identity of this tensor product which is your field K. So V, any vector space V tensored with a field there is a natural isomorphism. This is not just any isomorphism, this is a natural isomorphism to V, and K tensor V is also naturally isomorphic to V. So this is a structure on the category of vector spaces that you have, and yeah. So if you look at the tangle category, you similarly you have a tensor product kind of structure. So there is another way to compose two tangles. So if I have another tangle which is another cube, then I can keep one cube on the side of the other cube, and I can fuse them to get a new cube, and then I'll get a new tangle. So given two tangles, I can define that as a tensor product of two tangles, and then there is a similar identity there, which is the empty tangle. There is no tangle inside, so then you get the same thing back. So there is a natural isomorphism in that category. So the
composition is different than the tensor here.
yeah, there the tensor product is disjoint union.
Oh, so they are different tensors.
They're just different structures, but they also define the structure called monoidal category. So that is we will abstract this structure as we will call it a monoidal category. If C is a category with a thing called a tensor product, it's a functor from C cross C to C, and with an identity which satisfies the such that there is a natural isomorphism for any object in this category. So and then there is a coherence condition and all, which I am going to suppress just for the sake of clarity. I don't want to give too many details. So so the same thing works for the frame tangle category, and you can see that the frame tangle category is a monoidal category. Okay. And in the category of vector spaces, there is another structure that is interesting, that given any vector space, I have a dual vector space. So now I am going to restrict to finite dimensional vector spaces. So the dual is another vector space, and given any morphism V to W, I have a dual morphism from W star to V star. So so there is another operation called dual, and then so this and this really interacts with this monoidal structure. So I would like to define two maps. So given V star and V, there is a unique pairing. There is a natural pairing between every element of V star and V. You can naturally pair them and get an element of your field by something called evaluation. It must be clear. Like if you have a element, this is uniquely represented by. So you on the pure tensors, you can define it by the natural pairing. So this is the evaluation map that I am talking about, and another so there is a co-evaluation map over here. So this is why I restricted to finite dimensions. So if a V has a basis even up to En, then you define the co-evaluation map from your field to V tensor V star. This map is going to be one. So every map on this is determined by where you send 1 to, and 1 I am going to send it to summation over k ek tensor the dual ek, the dual of this basis element. So this map is what I call as the co-evaluation map. So the dual structure is really given by these two maps. So the dual so this is what we call a monoidal category with duals. So if you have an evaluation map and a co-evaluation map, so that these two properties are satisfied. So if you take V, and then from V, V is naturally isomorphic to V tensor. Okay, I should do this carefully. So V is naturally isomorphic to K tensor V, and then K. Okay, I will. And then I can apply co-evaluation on K, and then I will get V tensor V star tensor V, and then I apply evaluation on both of them, and then I will get V tensor K, and then V tensor K is naturally isomorphic to V. And you can see that if you start with a vector x, you will go to 1 tensor x, and then this goes to this particular element, and then you apply the evaluation on this, you come back to the identity of V. So this diagram commutes, and for the dual you have a similar picture that so V dual this is isomorphic to V dual tensor K, and then you can go to V dual tensor V star by co-evaluation, and then you apply evaluation on first two, and then you get to V star tensor which one? This one? Yeah. This is an isomorphism. So I have both way I have a natural map. Yeah. Both ways the map is natural. So so I have a map from here to here, and this is V star, and this is also identity. This can be verified in terms of a vector space maps. And now here what I want to see is that do I have evaluation, so do I have a dual structure to the frame tangle category. So what is going to happen is that if I have a tangle, so first let's look at without the tangle you have just these boxes, and then once you if you have a word in this category, that is going to be a word in pluses and minuses. Okay, so I will say I will rotate the cube. Okay, so then pluses will become minuses and minuses will become pluses. Okay, and then so this is a natural candidate for my dual. Okay, so so the tangle, so dual of a morphism would be dual of a tangle, which is tangle rotated. When the cube rotates, the tangle also rotates. So that is going to be my candidate for duals. And you can see for evaluation and non co-evaluation, I need candidates. So so evaluation is a map from. Yeah, so in the frame tangle category, the identity is really the empty tangle, which is so empty tangle. The the empty word. Yeah, the
So,
yeah, that's
so
my K.
empty to empty morphisms are all those links that in between things.
In between links. So
Morphisms of the
Yeah,
links.
yeah. So you can see every word is generated by this thing called plus and minus. So I'll define dual. So dual of a plus is a minus. So I need a map from plus minus to empty word, and then this I will choose as this this tangle. This is why I was making noise about this orientation reversing thing. So if you take a rectangle and without twisting you connect it back. So if you have an orientation like this here, this would be in the reverse direction here. So this will be a morphism from plus minus to the empty word. And this will be my candidate for an evaluation, and this would be my candidate for a co-evaluation. And then if you see that that commutative diagram that I drew over there, so I will start with any vector any. So let's say V is your plus. So I'll start with V, and then I'll go to V with V tensor V star, and then I will evaluate V the first two, and then this is my evaluation, and then this is identity. And the commutativity of the diagram says this must be same as this, but then this is a tangle identity. This is easier, and you can show that the dual one is like this. So the tangle category naturally has a monoidal structure with duals. Okay.
So your evaluation map, does it have like a half twist? How do you get?
No, there is no twist. Just the rectangle with the blackboard framing. No twist.
So the same thing is you are
Yeah,
changing
just
the
a
orientation
rectangle.
of the top line.
So
right
so
side.
if you start with a rectangle like this, so if it's oriented like this, then this would be oriented this way,
this is
and then
plus
you will
to
come
plus.
back, right? So this will be like this, then this will be over like this. So a rectangle is a natural choice for a map from plus minus to empty.
So this is like plus to plus.
No,
There is no
that's
difference.
from plus to minus. That's why I was saying that in a rectangle this thing is opposite. So when you connect it like that, you get a map from plus minus to empty.
The dual representation that corresponds to when you change this switch the orientation.
No, dual is so plus is minus, like dual of plus is minus. So you should see it as a rotation of the cube. So dual of a tangle will be the rotated tangle, and then the double dual is going to be double rotation, and the double dual is naturally isomorphic.
And so when you are doing evaluation, what exactly are you doing in terms
Of tangles. No, it is so evaluation is a morphism in this category. So the morphisms there are just tangles. So my evaluation is going to be that tangle,
Yeah.
which is a minima, and the co-evaluation is the maxima. It's just two tangles, and then that satisfies this commutative diagram. It's just a tangle identity.
Suppose in case it had some annuals, just randomly, so it's not the evaluation, it's a different map. Or
Yeah,
it's a different
that
map.
won't satisfy these axioms, no? So I will choose this as my evaluation, then it works. So the tangle category is a monoidal category with duals, and Yeah, and so all this structure is fine. So then if you had noticed, if you were careful, you would have noticed that evaluation and co-evaluation, that I have chosen a specific order of writing the dual and this function. So this is V star tensor V, and here I wrote V tensor V star. So typically, so this for vector spaces it's fine, it's easy to see. But then any arbitrary category, if you choose this order, then this is called a left dual structure, because the dual appears on the left in the evaluation map. So you can guess what is a right dual structure. The same kind of thing with everything flipped, and you have these two commutative diagrams. So then in the category of vector spaces, there is a natural way to construct a right dual structure. I mean, the same thing will work, but then you know that every map should be flipped. Okay, that is because you have a natural flip morphism in the category of vector spaces. Given any two vector space, it is similar to commutativity. So in the category of vector, so this is a structure on a category. It is not going to be very similar to a structure on a set. So you should be a little careful, but this is the corresponding version of commutativity. So on the category of vector spaces, you have tensor products, and then if you have two vector spaces, then from V tensor W to W tensor V, you have a natural map called the tensor flip, where X tensor Y goes to Y tensor X, and this is a this works as a flip. And then you can see that every map I can compose. So from V tensor V dual to this thing, I have a tensor flip, and then if I compose it with this, I'll get a right dual structure. So I can obtain a right dual structure on the vector space category by using this tensor flip map. Okay. Yes. Another thing to notice. So right dual will be you need to have an evaluation map from V tensor V dual to K, right? But
K to V tensor V dual.
That is co-evaluation, no? Yeah. So in the co-evaluation, are you asking for the co-evaluation?
You just said using the flip you can get the co-evaluation.
And evaluation for a right dual. So I will compose the
Even
flip,
that dual, using flip, you can get right dual.
a right
Right
dual
dual is the
structure.
co-evaluation.
Yeah.
No,
Right dual is an evaluation map from V tensor V star to K, and K to V star tensor V. So I will compose everything with the flip map, and then I will get a right dual structure on the category of vector space. That is because I had this morphism called tensor flip in that category. That may not exist for every category. So this is precisely the next structure that we are interested in, and this is called a braiding structure in a category. So if a monoidal category has such a structure, then we call it as a braided category. So a braided monoidal category is going to be a category C with which is given a natural morphisms of this form. So for every element V and W, there is a natural map called sigma VW from V tensor W to W tensor V, which satisfies a certain coherence condition, and you can show that which satisfies a coherence condition. And then over here, what I need is that for every object, so here I would define this tangle. So I need a candidate for the braiding structure in the category of tangles, and then this is going to be my model. So this tangle I would choose as my braiding. So for the tensor flip in the vector space category, I would suggest this tangle to be my flip map. So you can see that like this can be extended to any you can give different words, and you can write down the flip map. So once you write it for a simpler object, you can extend it to any word. So you can write down the flip for any word using that tangle.
Is there a difference between flip and braiding map?
No, it's a generalized version of a flip map. That is, this category may not be a category of vector spaces. So I mean, it can be the tangle category, for example. So that is not a tensor flip map which is defined over a vector space. So I'm just abstracting structures from the category of vector spaces. So in the category of tangles, that maps will work as a braiding. So I have a braided structure on the category of frame tangles. As I told you, we are going to construct structures on the frame tangle category, and then we will look at the right notion of a representation of that category. That's what we are trying to do here. So this is a braided monoidal category, and then once you have this, there is a nice thing that you can do. So take an endomorphism. So let's say V to V, I have a map called F. So then in this, I'm now back in the category of vector spaces. So now you take your field K, and then from K you go to V tensor V star by the usual evaluation map that you had, and then co-evaluation map, and then you apply F on the first component. So F tensor identity on the second component, you come back to V tensor V star. Now you do the tensor flip, and then you reach V star tensor V, right? And then you do the evaluation map, and then you reach K. So for every morphism, every endomorphism F of a vector space V, I can construct a map from K to K, the identity object, and then if you try to see where one goes under this map, the image of that is a scalar here, and that is precisely the trace of this endomorphism. So the trace of your endomorphism in the category of vector spaces can be represented by this morphism from K to K. So I would define this as an abstract notion of a trace. So you can abstractly define it in any category, any monoidal category with a braiding. You can define a trace in this way. Okay, so yeah, this should be really seen in terms of the previous lectures. The trace is what we are always interested in. Like trace is going to be our invariant. So we need the notion of a trace in a general sense. So in a braided category, you can attempt to define a trace in this way. So you see here, what we have done is that after coming here, what we have used here is the really the right dual structure, the right evaluation. In the category of vector spaces, this coincides with your right dual structure, right? But then you still do not have a right dual structure in a general braided category. So I'll show you the problem of constructing. So this is a really good way of looking at it. So if you have an evaluation, this is already a monoidal category with duals. So you already have a left dual structure. So from left dual, you can construct a right dual by saying that this is, I'm going to compose this with a flip. Yeah, the braiding. So this will give you a right dual structure, but this is not this is not topologically right. Why that is not right is because so you should look carefully into this. Okay, there is a metal thing over here. So this is really what we are doing is that we are composing it with a this tangle, and then we want to construct a right dual structure. So this is my usual evaluation. Okay, this thing is on the left, and now I want to the right dual that we have constructed is really this, right? So we composed it with the braiding, and then we evaluated the usual evaluation. But then if you see, this is not same as this has a twist. This is topologically not the trivial rectangle. So what you can do is that you can put you can put another twist. Opposite curls cancel. Right. So the way to so you have just put a twist like this. That is a naive attempt. That the way the topologically speaking, you should really have that extra additional twist which will cancel this effect of this twisting. So yeah, so that is what the final missing tint, and that structure is what we call as a ribbon structure. So that is what we will call as a ribbon category. So to say what I have done is really this. So in the category of tangles, yeah. So this was my choice of a right dual. So instead of this, what we actually wanted was so this with an extra twist like this. Okay.
If you fix your endpoints, then the opposite curls don't cancel, right? If you fix the endpoints,
Yeah.
you need S2. You need some kind of sphere.
No, the opposite curls always cancel. You can you take something like this and then twist it like that. So opposite curls always can. You need not move these points.
Don't you need a framing on the point on the endpoints? So you're allowing
No,
twisting.
basically these twists that you're doing is actually like you take a string and then twisting, putting a full
Are you
twist.
allowed to twist at the endpoints?
No, the endpoints need not twist. So in between you put a curl, and that will mean you put a full twist in the positive direction, and then the other curl is going to be a full twist in the negative direction, and they will cancel in between. You don't have to move the
Don't have to-
endpoints.
Okay.
The endpoints are unmoved in this entire process. So this is our candidate for a right evaluation with an extra twist. So for algebraic reasons, I need to put this twist inside this. So it's a little complicated, but then this is how it is. Maybe I have drawn it wrongly, but yeah, you got the idea. I've just changed this twist into that twist. So this is what we will call as a ribbon structure. So abstractly, a ribbon category is a braided monoidal category with an extra structure, so that for every object V inside your category C, you should have an extra natural natural invertible, an automorphism of V, which we call as BV, from V to V, which satisfies the following properties. So this should respect your tensor product in the following way. So BV tensor BW should be B of V tensor W composed with sigma VW composed with sigma WV, and this is really a nice topological exercise that you should do. That the first identity that I have written down translate to this. So this is my BV tensor. So this twist is going to be my ribbon morphism in the category, and this this is BV tensor BW, okay, and this is same as and then 2 twists. So you can see that these two tangles are the same. I mean, it's just
But the top one should go behind.
yeah. You can work it out, like you just push it here and then move it down, and then you do 2 Reidemeister move 2s. So you can see that these two tangles are the same, and that is my first axiom of a ribbon structure. So BV tensor W, this should be this, and then if you take a dual, so BV B of the dual must be same as BV dual, and for the identity element, B of the identity must be same as the identity morphism of the identity element. And so this is what I call as the ribbon structure on the category. And yeah, and so if you choose this as your ribbon morphism for plus and minus, you can write down the same thing. So then this will give you a ribbon morphism for every object in your category. and under this structure the category of framed tangles is a ribbon category, and this is the ultimate structure that we are interested in. So, so we would be interested in representing this category over any algebraic categories. So now let's look at a very interesting thing which happens here. So oh yeah. So this is same as that, and then I can push the entire crossing. And then I have those maybe I have twisted it differently. Yeah, yeah. This is not same as that, no? No. Yeah. Sorry. So now this is just Reidemeister moves. Right? So you can. I mean, first I can just pull it apart, and then the second one also can be pulled apart. So this works. So in a ribbon category, we have a better notion of the trace. So that basically means I have a better idea of a right dual. So which is given by this map. So I'll start with V tensor V dual, and then I'll apply this ribbon morphism on V. So for some technical reasons, I'll apply the inverse of this and identity on this, and then I'll reach here only. V dual, and then we will flip it using the braid map, and then you will reach V star tensor V, and then you apply your usual evaluation to K, and similarly with the co-evaluation. So this gives you a nice this gives you another notion of a right dual, and this is the one which is actually we need. So for giving, I mean, you should attend the next lecture, then we will see why this is the actual notion of a dual. So so giving this as a right dual map, now I can define a similar trace. So if I have an endomorphism of a vector space of a map V, then from the identity so I can go to the usual co-evaluation by this thing, and then I'll apply the function, and then I'll reach V tensor V dual, and then I will apply the right dual that I have just constructed, and then I'll reach K. So this map from identity to identity is a natural choice for my trace, and this we will call as the quantum trace of F. Right? And in a general category, I'm not this need not be just vector spaces. So in a general ribbon category, you can define the trace of a morphism, of an endomorphism of any object by this form. It will be a map from your identity object to identity object. It can be anything. In a category of vector spaces, this will be of a nice form, and it will match with your idea of a trace. And it's a very well-known fact to knot theorists that there are these things called elementary tangles. so those are going to be, so just the identity and this and this flip and all their cousins. That means you reverse orientations and so the opposite twist, and so all things that you can make from these things. So these are called elementary tangles, and all their orientations together will generate the whole tangles that you can have. So any other tangle can be obtained as a tensor product and composition of these tangles. So these are like our elementary tangles, and you can see that whatever we have done till now, these things were the structure maps of a ribbon category. This was our identity, this was our braiding structure, this was our evaluation, this was a co-evaluation, and this was the ribbon structure. So all the structures that we have just defined is correspond to your elementary tangles, and the plus is an object which will generate the whole objects in your category. Taking dual, you will get minus, and then you just take tensor products. So you get every object in your category by just plus, and every morphism in the category is generated by the structure maps. So in a sense, this is a very this is the most freest example of a ribbon category that you can have. And now if C is a category, is a ribbon category, and then if you have an element V of the ribbon category, then by sending plus to V, and then these corresponding morphisms to the corresponding structure maps in your category. This is an exercise that this extends to a unique functor which respects all structures in your ribbon category. So these will go to the corresponding structure maps, and then every tangle can be broken down into these pieces and their tensor products. So you get a functor which respects the tensor structure, the braiding structure, and the ribbon structure. So that unique functor that you obtain from V, so I will denote it by FV, and this is called the Reshetekin-Turaev functor.
This is from Tangle category to any.
To take any ribbon category and an object in the ribbon category, I have a unique functor. Right. So this is like, this should be really seen like a free. So if you have a free module generated by one object and take any other module and fix an element of the module, there is a unique map. There is a unique module map from here to here, which sends the generator into that. So this should be really seen in that sense. So the category of frame tangles is the free example of a ribbon category, and given any other ribbon category, you have this thing. And now if you look at, as I pointed out in the beginning, if you look at 0,0 tangles, those are precisely your framed links. So the Reshetekin-Turaev functor will send it to some morphisms in the from some n-fold tensor product of V and V duals. So you get a morphism from I to I in the category that you have fixed, and that is an invariant. So in the next lecture I will show you that almost all the invariants that we have seen arise in this way. So this is a categorical way of looking at invariants. So that is why ribbon categories are important, and now the idea is to look for ribbon categories. So in the next lecture I will show you how representations of a quantum group forms nice ribbon categories. And one more thing I want to notice is that if you take a category of a group, representations of a group G, then this has all the structures that we have just discussed. You can make a tensor product of two representations and another representation, and the tensor flip is a G module map, and the braiding you can choose that gives a braiding, and then you can choose the ribbon structure to be just identity morphism, and everything works out. But then the problem with that category, so that's a ribbon category, but then the problem with that category is that the flip has a property that twice flipped is same as your identity. You are not doing anything. If you flip it twice, then nothing happens. So this means that in our ribbon category, so this is my flip, and then if I do it twice, so I get a tangle like this, and the functor won't recognize between this tangle and the identity tangle. So these both will be sent to the same morphism. So the invariant that you derive out of that Reshetekin derived functor is not going to recognize between this tangle and this tangle, and that means so you when you have two strings which cannot be pulled apart, and if your invariant is going to see this as this, then the invariant is trivial. So you are going to get a trivial invariant. So from the category of groups, the invariant that you can get is just trivial. So we will quantize such a thing, and we will get a category of representations of a quantum group, and then we will show that there is a nice ribbon structure which will give us nice invariants. So yeah, that's all. Thank you.
Your questions?
Will be minus minus plus minus. So now once you have a dual, so you can use the evaluation co-evaluation maps. So if you have a morphism from V to W, then you look at W star, and then W star you can send it to W star tensor V star, and then you apply F on V, and then you reach W star tensor W tensor V star, and then you apply evaluation on this evaluation of W, then you reach field tensor V star, and this is isomorphic to V star. So you get a map from W star to V star, and this is really your dual morphism that you get. So you need, for every morphism from V to W, I need a notion of a dual morphism in general. So here my morphisms are tangles. So I need a dual morphism from that a word like that, and I need to get a dual morphism. And then the natural choice is to rotate the tangle. So then all pluses will become minuses in below also, and then the tangle will be a tangle between the duals.
So the way you say that frame Tangle category is like a free category, like in a sense.
Yeah.
So any other ribbon category can be thought of generated by.
No, any other ribbon category with the choice of a object in that category. There is a unique representation of that ribbon, the frame category. Any ribbon category and the object in the ribbon category, I have a unique functor.
So the empty category can never be a ribbon category because we cannot choose any.
The empty category, okay, that is the ribbon category, but there is no Reshetekin derived functor because there is no object. Yeah, we rotate and then you rotate. Flip the.
No, I think that is this have to do this rotation, right? You don't have to do that rotation actually.
But my pluses should be.
But then the diagram of the rectangle that you draw.
Yeah, you can just start with this rotation.
But you also need a V-star, V-star to be filled.
Yeah, that I also want.
V tensor V star is not. Yeah, there's a morphism. Yeah. The evaluation. In the tangles, that is that is this model.
They,
That one.
the evaluation is the third one.
So this is my usual evaluation, the minima, right? And then I'm composing it with a twist. So the minima, I first twist it, and then so that is this one. That was a naive attempt, but this had a twist. So we put an opposite twist, and then you make it into a. That is my right.
This is a non-canonical choice.
This is a canonical choice if you think topologically, but then algebraically you should have just used the braided structure. But in this category, it's not the same. I mean, you would have chosen the natural, the minima in the opposite direction to be the dual evaluation. But then that is not. This is not same as composing it with the braid. You need to put an extra twist, a kink, and that is the ribbon structure.
What if you want to put two kinks in and do it two opposites? There are choices.
If you put two kinks, that's not going to be trivial. Like there is already a kink. This is the algebraic solution.
You're saying this is a canonical.
If you think topologically, this is the natural way to cancel that twist that you will. So you put the braiding structure and then use the usual evaluation. Then you get a twist, and to remove that, the natural way to do it is like put an opposite structure.
So the ribbon structure is not there in the category of vector spaces?
Yeah, the trivial ribbons, even the vector spaces category, this works out, no?
Yeah.
From the category of groups, like finite dimensional vector spaces, yes.
So B to B just take identity.
Yeah, that will work as a ribbon. But the problem is wherever you have this thing, that the braiding is trivial, so that won't give you a good invariant.
So in case of category of frame tangles, we have this curl as this tangle as a ribbon.
And the quantum trace should really be seen as identity in the tangle category is just empty object, and this is also empty object. So you are basically the function is something which happens in between. So you're basically it should be seen like a vacuum amplitude kind of thing. Like there was vacuum, there was nothing, and there was nothing and in between something happened. Some particles came and interacted, and then they went. So you're measuring something which happened.
We can take 5 minutes break and then the discussion.